Well, hello everyone. Time for us to finish off hypothesis testing of the difference in two proportions. So essentially what we're going to do here is look at how do we find if there's evidence to prove that two distinct populations proportion value, whether they are the same or one is bigger than the other or one is less than the other. So let's imagine we have our two populations. And this is going to be population 1. Population 2. Now, the guy that we're interested in finding is the population proportion P1, and this one here is the proportion P2. But what we're really more interested in is how the two of them interact. So we're interested in finding the difference in these two. So far, so good. Well, if you want to find the difference in these two, what would the hypothesis test look like? Well, the null hypothesis is always going to be that the difference is 0. In other words, that they are equal to each other. And the alternate hypothesis has 3 possibilities. And it's written always in this way, that the difference between the two is greater than 0. That the difference between the two is less than 0. And that the difference between the two is not equal to 0. This one here, this first one, is a right-tailed. And we're essentially wanting to prove that the first thing is bigger than the second. This one is called left-tailed. And the opposite is true. And this is called two or both-tailed. What we're trying to prove here is that they're just not the same as each other. So one of these 3 alternate hypotheses is always going to happen. Either this one, this one, this one. And this guy here is the only null hypothesis. So how do we go about finding evidence to prove that one of these 3 is in fact true? Well, we find a sample P1, and we find another sample P2, and we work on the data that we get from these to see whether or not there is any evidence. Now, how's that going to kind of work itself through? Well, let's take an example and kind of keep it general for a little while and then tell you how it works in particular. So we have these 2 populations. We find our 2 samples. Each sample might have a different sample size, N1 for the first population sample and N2 for the second. Right. So we're going to find a thing called the test statistic. And the test statistic is essentially the difference between the 2 sample proportions. Now we're going to find the standard error for the difference between these 2. And the formula, you may recollect it, will look something like this. Notice that we're using the P1 the sample version rather than the population version. And the reason for that is that we don't actually know P1 and P2. If you notice here that what we are assuming that they're either the difference is 0, which means they're equal, or one of these three is alternate to it. But nowhere do they mention that it's equal to 0.4 or anything else. So we've got our test statistic. We calculate our standard error. We then get a guy called the z-score. And the z-score takes on this value. Now, if that z-score is unusually large or small, then it will be evidence that one of these three is true. And then you calculate the p-value, which is going to be the probability that you get a z-score. And that z-score is either going to be greater than or less than this number here. And then finally, we do our test. And the test is our p-value less than the significance level of? And if the answer is yes, then we have in fact proved that one of the alternates is true. And if the answer is no, then there's not enough evidence. And that's essentially what the generalized structure to how we are going to do this. So let me begin by doing one from scratch, at least as much from scratch as we can. So let's suppose that we have two populations. Population 1 is males. Population 2 is females. And in population 1, we have 200 people. And population sample 1, we have 200. In sample 2, we have 250. And we ask them, do they like Pepsi more than Coca-Cola? And for this group, it's 150 out of 200, which is 0.75. And in this group, let me check something on calculator. We get 180 out of 250, and that ends up being 0.72. In this story, we're being asked to see if there's enough evidence to show that males like Pepsi more than females. Using significance level of 5%. Well, our little kind of hit list of things to do. I'll show you them. Let's set up our null and alternate hypothesis. I guess it would be step 0. Well, the null hypothesis is simply P1, population 1, take away population 2 is 0. And is there enough evidence to show that males, that's P1, is bigger than females P2? So we're looking for that. Statistic is P1 hat, take away P2 hat, which is positive 3%. So we're quite happy of the evidence that seems to at least be pointing in that direction. Standard error. A little bit messy, but here it goes. 0.75. One take away that number over a sample size of 200. And then we have 0.72, 0.28. Can we do that one over 250? Let's see what we get here. If I square root of 0.75 times 0.25 divided by 200 plus 0.72 times 0.28 divided by 250. And the answer we get here is 0.0418 to 4 decimal places. I get our z-score, which is essentially the number that's going to tell us how unlikely this data set is likely to happen if the null hypothesis was in fact true. So we're looking at 0.03 over 0.0418. 0.03 divided by 0.0418, and I get 0.718 to 3 decimal places. So we now find the p-value. And it's essentially, what's the probability that you get a z-score? This number or bigger? You might say, well, I don't know it's bigger than this number because the alternate, so no, the alternate is greater than. It's a right tail test. Now this guy here really has to be done using salt. So you hold on for a second. I'll hit salt. We'll bring this guy over. And what we want to do is we want to find the probability that z is greater than 0.718. So greater than is right-tailed. 0.718. You could put it there if you like. And the answer we got is that guy, and that's your p-value. So your p-value in this case is 0.236. Now we'll move and return back to our notes. So, step 4 there. Let's go. Step 3. Standard error. Step 2. Test statistic. Step 1. Set up the null hypothesis. Step 0. So, time to do conclusion. Is our p-value less than significance level of? Is our 0.236 less than 0.05? The answer here is no. So conclusion is not enough evidence. To reject null hypothesis. So in English, you would say there's not enough evidence to show that males like or dislike Coca-Cola more than females. And that's essentially from start to finish the entire process by hand. Now there are a few other things I would like to mention before I go and look at the homework. And one of them is, when are we allowed to use this process? Well, of course, you need the data to be unbiased. You collected it from good samples representative, but you also need all these to be true. Remember the 10 rule. And provided this condition is met, then you should be able to continue with this process and come up with a valid hypothesis test, and then at the end make your conclusions, and they would be accepted. Okay, what we're going to do now is we're going to look at some homework questions and see what they look like. So, let's see. Okay, let's see if we make this a little bit bigger. And we'll start at the top. Okay, no answers. Okay, so one example of a possible hypothesis test of interest is whether or not the proportion we get a particular disease is the same for two different age groups. So what are the populations of interest here? The population are everyone in the two age groups who could get the disease. Basically, the population is everybody in the two age groups. So it's that one. Now, once we know who each age group is, let's say it's 30 to 40s and 60 to 70s, then we would look at what percentage, right, what proportion in each group got the disease. The parameter of interest, okay, so that's going to be the difference between the proportion in the first group who get it and the second group who get it. So the population parameter is the difference in the population of the people in the first group who get it and the people in the second. Now, P1, take away P2 equals 0. I'm going to put on the key here. Just to make sure. Here we go. Yeah. You may have to do subscripts. I'm not 100% sure, but if you do, if you put the answer in and P1 take away P2 equals 0 isn't working. Because if you look here, do you see how the 1 and 2 is smaller than these? Which is why I suspect we may have to do subscripts. So let's sign up what we have here. It's not that one, that's for sure. Subscripts, operations, functions. There we go. Subscripts, that one there. So we're going to do P subscript 1 take away P subscript 2 equals 0. Just in case. Bear that in mind, that you may have to use a subscript to make WebAssign happen. Define the parameter P1, P2 to be the difference in proportions of 21-year-old men and women in the United States who have a high school diploma. Researchers are interested in the hypothesis that they're equal. So the population, in this case, are all 21-year-old men and women, and we are interested in their being the same as each other. And I am now going to take off those guys as they are a distraction. Now, in each part of is the statement valid null hypothesis. In a sample of students, the mean pulse rate for the men is equal to the mean pulse rate of the female. The key word here is that they mention the samples. Now, null hypothesis and an alternate hypothesis are all in terms of the population parameter P1. We use the sample to test it, but the hypothesis itself is in terms of the population value. The average weight of newborn boys is the same as the average weight. Well, that's not a valid one either. So it's no. The proportion of cars in California are white is higher than that in Maine. Yes, that is allowed. Now, the next question says state the null and alternate hypothesis for each of the following research questions. In each situation, also indicate whether the hypothesis test will be one-sided or two-sided. So one-sided would mean right or left tilt. And two-sided is the not equal to situation. So the question is, do female college students study more on average than men? Well, the null would be the same, males and females. And the alternate would be that the females more than the males. So let's see which one of them that works into. Okay, here we go. Do female college students study more on average than males? The null is that they study about the same, and the alternate is that they study female study more than the males. That here is a one-sided test. It's actually a right-sided test. Compared to men who are not bald, are bald men more likely to have heart disease? So we're looking for bald and not bald, and are bald men more likely to have heart disease than non-bald men? Okay. So we need to find one that essentially says that in the alternate. So the null hypothesis is going to always look like this sentence. And there's lots that have that sentence. Bald men who are not bald are equally likely to have heart disease. And then the alternate is bald men are more likely. So bald men are more likely to have heart disease than men are not. And so we're looking at that one. So there it goes. The null hypothesis is that they're equally likely to catch heart disease or have heart disease. The alternate one that the statement up here is stating is that bald men are more likely to have heart disease than men who are not, and that is a one-sided test. This one here says, is there a correlation between height and head circumference? So in other words, that they are either equal to or they're not equal to. So the first one is there's no correlation, and the second one is that there is. It's this one. The null hypothesis is that there's no correlation between the two, and the alternate is that there is. And that is a two-sided test because it's got essentially that they're not equal to each other. Right, we now are looking at calculating p-values. So all the information that we need is here. If you look really carefully, you see it's a less than and a z. So when we hit solve, I'll see if I can shrink these down. And I'll go in and out just to make sure that take me a few moments to hopefully shrink the window down to appropriate size. There we go, and then I'll go in and out to make sure you can see it. So we're going to use salt to find the p-value. All right, so we're looking for a less than. You can tell by going here. So if I shrink this little guy down, should be able to, can I see the downtime? Okay, we're on the usual fighting the Windows game. Okay, I'll try it this way. Oh. So we are interested in less than 0.54. So less than, set up 0.54. There we go. This is the p-value. I'll copy it. And put the p-value in here. That's a very big p-value. It's definitely not less than that. So do not reject a null. Right, next one, greater than 0.54. I think that's going to do much better. Sign out. Right field, greater than. And the answer we got is this fella. And that is definitely not less than significance of 0.5, so we won't reject it. We're looking for a less than again. Here's our Z. Less than. Negative 2.17. So less than negative 2.17. The answer we get for our p-value is this fella here. Now, is that guy, interesting, it says 4 decimal places. That's all it is, okay. Now, is this less than 0.05? And the answer is yes, it is, so we can reject the null. Now, you want it to be greater than 1.74. So you want greater than, right-tailed, 1.74. The answer I got is that p-value there. And I'm looking at that guy, and he is also less than 0.05. So as long as your p-value is less than the significance level, you can reject the null hypothesis. And so the alternate is true. You've actually found what you thought was true. Now, here's our next one. During the coronavirus pandemic in 2020, restrictive measures were enacted to keep people from interacting with each other in public places. Polls asked the following question in the 3rd week of April and again in the 2nd week of May. Do you think that current restrictions on how restaurants, stores and other businesses operate in your state are appropriate? Or are too restrictive? Or are they not restrictive enough? They had 2 different random samples of 1,007 individuals. And in April poll, 18% said they weren't restrictive enough. Well, in May, it was 22%. Now, did this proportion of the population who thought the current restrictions were not restrictive enough change? So we want to know, are they different from what they were? And all the hard work has been done for us because that's the only number that matters. And we're interested, are they different? Now, P1 is the population proportion in April, right? We went and said not restrictive enough. P2 are those who basically did the same thing, who said it's not restrictive enough. And it's to do with populations, not samples. P1 is to do with population 1. P2 is the next one. So the null hypothesis is that the difference is 0 because it's always going to be that situation. So let's say we can do that. P subscript 1 take away P subscript 2 equals 0. Your null hypothesis is always that, not going to change, no matter what the story is. We assume that they are equal to start with, and then the alternate is evidence that something different is going on. Now, in this case, they want to look at they are different. So different is going to be P1 take away P, in the wrong place. Take away P. Okay, got to be careful with how many subscripts I've got going on here. Just start from, can't really see when we're, so I've done it again. And I've done it again. It's a pain, isn't it? P1, get out of there. Take away P. Okay, for some weird reason, I'm just making life harder than it truly is. Why am I doing that? Why don't I just copy these two? Got the first one right, there we are. And we want it not equal to. So provide the numerical value for P1. The numerical value for P1 is 18, 0.18. And for P2, 0.22. Now I'm saying that they are different. I guess I could also have said that P1 is less than P2, in which case I would change that. So let's see what they said in the story again. I'm just reading through it. I'm assuming that they're different, and that's why I'm going for the not equal to. Now, the p-value for the test is given as that number. Correct, it is. Write a few sentences explaining what the p-value means in the context of this situation. Yeah, it looks like a lawyer got to this one. Okay, so the p-value is the probability of observing a difference in the sample proportions, at least as large as the one that we observed if there was no difference in the population. So if they were both the same. That was a bit messy, but I'll take that one. What conclusions can you make? Well, at a significance level of 0.05, this fella is definitely less than. So the p-value is less than the stated significance level of 0.05. So there is sufficient evidence to reject the null hypothesis. So there is strong evidence that the population will be thought restrictions on how restaurants, stores, and other businesses are not restrictive enough changed between the third week and the May week. In large samples at each time period, the proportion we felt the wave increased from, let's get the numbers back in, 22 and 18. Which one was April? 18. So 0.18. Or we won't need, it is percentages, so I should put in all numbers. So it's 18, 22. And the size of increase in proportion in these two samples would be quite unlikely if the population proportions had not changed. Which is what we do in hypothesis test. If p-value is unusually small, less than 0.05, we can make the sensible conclusion that since this is quite unlikely to have happened if P1 and P2 were equal to each other, then this must be evidence then that they're not equal to each other. In this case, exactly not equal to, but in other situations, the reason they're not equal is one's bigger than the other or one is less than the other. Okay, everyone, what we're going to be doing is continue with our work. Question 8 then, halfway through roughly. A survey was conducted in which they asked college students whether they would return money if they found. And there's a group of women, 93 of them. 83 said they would return the money. And of the 75 men, we are looking at 57 of those. And significance level is 5%. Alpha equals 0.05, which is here. And we are going to test the null hypothesis, equal proportions of students who return the money versus an alternate that the higher proportion of women would do so, and let one be women. Okay, so when population 1 is women, population 2 is men. Let's get this shown the right. So the null hypothesis is going to be P subscript 1, take away P subscript 2, and that is always equal to 0. And we are interested in the fact that women are more likely to return the money than men. So 1 is bigger than 2. So P1 take away P2 is greater than 0. So that is a right-tailed test. Now, all the information that we need can be calculated now doing SALT, including things like the test statistic, which is basically P1 take away P2, the p-value, and then our conclusion. So SALT's going to do all the heavy lifting for us. So let's click on that. I'll bring this over here, and we're going to do inferential statistics, and we're going to do 2 sample proportions. So when you get a question like this, where you're basically going to do everything from start to finish, choose inferential statistics, 2 sample proportion. Now the first sample is women, and it was 83 out of 93. And for men, it was 57 out of 75. And our hypothesis test is that women are greater than 0, greater than men. And then we generate results. And so the difference in proportion is this number here. So take that away. There we go. 2 decimal places, so I guess that's going to be 13. P-value now. Nice and small. There's our p-value. Into 4 decimal places. Well, that 9 becomes a 10, essentially. Now, since the p-value is less than the significance level, we would reject the null hypothesis. This means that there is sufficient evidence to conclude that a higher proportion of women than men would return the wallet if they found it. So here's our next story. In 1990s, ear piercing and tattoos became common among college students, in particular college men. Surveys of male students at a large university during that time period found of 423 men, with no pierced ear. Of the 423 men with no pierced ears, 42 had tattooed. Okay. And of 143 men, so the second group was 143. So there are 2 groups of men, those with ear piercings and those without. And of the 143 who did have it, 41 of those had a tattoo. Assuming that these men were representative random sample of college students in the 90s, here's our test now. College men with 1 pierced or more. had more likely have tattoos than those who had none. Okay, so P1 is going to represent use college men with an ear pierced, so they're going to be P1. That's going to be take away P2, those who did not have any ear piercings. So start that with zero. And we are assuming that P1, those with ear piercings, have more tattoos than the other. So verify that the necessary data conditions. Now the data conditions are the NP1 stuff and N1 minus P1 stuff and so on and so forth. Now there are two independent, and we're told that we can assume that they're random selected and that all of these ones are at least 10. So we should conclude that the thing is met. So test statistic, P1 take away P2, p-value, and then conclusion. So I'm now hitting use salt. We'll bring this over. Inferential, two sample proportion. The first one was the men with ear piercings. They are 41, 420, 143, and 42 out of 423. And first group, men with piercing, greater than percentage with tattoos and those who don't. And there's our results. And the difference is huge, about almost 19%. I'll fix the rounding off issue in a minute. P-value. Wow. P-value is tiny, that's fine. We kind of assumed that it would be. That's essentially 0, and that's 1.9. Now, since the p-value is less than the significance level, we reject H0, and then this means that there is sufficient evidence to conclude that men with at least one ear piercing are more likely to have a tattoo than those with none. And pretty much it's going to have that same format to it from start to finish. And this is, as you look, you can see this is pretty much the same. 11, pretty much the same again. So we move on to question 12 now. A case-controlled study compared the short to not short English secondary school students. Of 97 short students, 47 said they were bullied at school. And for 113 who were not considered short, 30 said that they had been bullied. Now, this fella here is pretty much going to be standard P1 take away P2 is 0. And we are interested then in setting up hypothesis test to prove this. The research wanted to know whether short students are bullied more often. So P1 is the short students, what percentage of them were bullied. So we want to see whether there's evidence to prove that P1 is bigger than P2. Now, if you can look at the information that's already given to you, the p-value here is tiny. So we are told to assume that the data represented the sample size are sufficiently large in both groups, and so we can conclude that the conditions are met. Let's do the test statistic, which is essentially P1 taken by P2, so it's that number. So really, it's a bit like SALT was done for us, and we just read off the information. The p-value is this value. I'll do some rounding off here, or do we need to? No. Now, since that p-value is less than the significance level, we reject H0. This means that there is sufficient evidence to conclude that short students are bullied more often. A 95% confidence interval is here, where at least they told us the lower bound. Now, what we're told is the lower bound, not the upper bound. Now, if you think about this guy is going to be in the middle, and this guy is on the lower bound, if I can find the difference between these two, so I'm just going onto my calculator and finding out what the difference between 0.219, 0.49. So I'm taking this number and subtracting that from it. And the answer I get is 0.107869. Now that tells us the difference between the middle and the center. So if I take, sorry, the middle and the lower bound, if I take the middle and I add this difference, 0.219049, I get the upper bound, and it is 0.326918. Now, if you were just going to make it this number and bigger, the alternate would be just to say or 1. Now, use a one-sided 90% confidence interval. Well, the confidence interval falls entirely above 0, which suggests that the null hypothesis should be rejected. So it doesn't matter if you use that number or that number, I'll come to the same conclusion. Okay, let's look at 13. Researchers want to test the effectiveness of a new antidepressant medication. In clinical testing, 127 out of 220 people taking the medication reported an improvement in symptoms of the people who got a placebo. 81 out of 230 have reported an improvement in their situation. Define the parameter of interest. Well, it's the difference between the two things, isn't it? And it's the proportions. Now it says calculate P1 and P2. So really I just need to do 127 out of 220. Then round that answer to, oh, as a fraction. Okay, I can do that. So 127 out of 220. And P2 is going to be 81 out of 230. State the appropriate null hypothesis. Well, I don't like it this way, but we're stuck with that choice. In this story, we're assuming the first drug is more effective than the second. We're almost done. So we've got these two guys. They're both the same, essentially the same at least. So I'll do this one and you can figure out the last one yourself. Studies have suggested that alcohol abuse and disorders are found to be more prevalent during early adulthood than in any other age group, with about 9% of young adults meeting the criteria to be labelled as an alcoholic. Wow. In addition, surveys have shown that college students tend to drink more than their peers who do not attend college. We want to test to see if there's any difference in excessive alcohol use in young adults who attend as these students and those who do not attend college. And the question they asked them was, have you consumed alcohol to a point of being drunk in the past month? So all the information that we want is essentially here. We have P1 being college students, and they have P1 of 96 out of 265, and P2 is the other, not college, and they are 42 out of 150. So we're going to use SALT, put all that information in. So to sample proportion, check. Number of successes. Well, success in this case is getting drunk. So 96 out of 265. And the second group is 42 out of 150. And we are looking at, what are we looking at? I'm assuming we're looking at that college students drink more than males, so that's going to be that's greater than. Okay, so we'll generate results, and the difference in proportion is extreme. So it's that number. The two decimal places is that number. Now, if the null is that they're equal and the alternate is oh that they're different, okay. Now, since they are different, I'm going to change my result just a little bit. And this almost negligible, but it did change it to 57. That's the first one, and the alternate is not equal. In our case, the p-value was tiny, so we will reject the null hypothesis. And thank you. And that is everything that you need to know, hopefully, to do chapter 12, hypothesis difference, hypothesis testing for the difference in two proportions.